Hello, everybody. Welcome to the presentation of our paper, With Whom to Communicate, Learning Efficient Communication for Multi-Robot Collision Avoidance. My name is Alvaro Serra-Gomez, and I'm a PhD student at the Cognitive Robotics Department at Delft University of Technology. To start with this presentation, let's consider a team of robots that must navigate safely across an environment. In order to do so, this team of robots are allowed to communicate and exchange their trajectory intentions. There are several decentralized motion planning methods that address this problem. Nevertheless, these tend to use expensive communication policies such as broadcasting or periodical communication exchanges, which may result in redundant or useless communication among robots. For example, in the right side of the slide, we can see a blue robot that tries to get to its goal. However, in order to do so, it will have to communicate with those robots that suppose a risk, meaning the red ones and the orange one. But those in green do not suppose a risk. Therefore, communicating with them is useless. This can be a problem, especially in scenarios that present communication bandwidth constraints, which motivates the research of efficient communication policies that keep these communications into a minimum and that can communicate and thus can communicate efficiently, especially those that can influence existing motion planning methods that use communication, thus profiting from already existing methods, and that can choose when and whom to communicate with the other robots in the team. Therefore, we can start formatting our problem by considering the following situation. For every time step t, every robot I state can be defined through its position and velocity, through the position of its goal, and the future trajectory intentions computed at the previous time step. The available information that it will have is the information of its own starting state and the positions and velocities of those robots that it can observe. Also, it will have available an estimation of the future trajectory intentions of those other robots it can observe, and whether these estimations are the actual computed trajectory intentions from the other robots or an estimated trajectory intentions computed through a constant velocity model will depend on whether we communicate or not with the other robots requesting these trajectory intentions from them. Whether we do this or not is embedded in the communication action, which is accompanied by the control input action, which will allow the robot to move through the physical space. In this work, we consider that we can decouple these two terms of the action space and solving the control input by formulating an MPC using already existing motion planning methods that use communication, and solving the communication action by using multi-agent reinforcement learning. Regarding the state of the art, we consider that our work is related to the following fields: coordination and collision avoidance, communication scheduling, and communication learning. In coordination and collision avoidance, we see communicating methods that present the limitations that we have already mentioned before, and there are already methods that try to cooperate while not using communication. However, these usually produce unsafe or very conservative trajectories. There are also those methods that use communication scheduling. These usually use receding horizon algorithms, which depend generally from the design of an heuristic function and might be limited by the prediction horizon set a priori. Finally, those methods that that try to learn the communication policy usually tend to learn the control input at the same time. Thus, they don't get to profit from already existing motion planning algorithms that work already well. Thus, our contribution is the presentation of a combined communication policy and trajectory planning method that can use the strengths of nonlinear MPC and multi-agent reinforcement learning, thus learning when and with whom to communicate in multi-robot collision avoidance tasks. First, we can see a summary of our framework in the following schema, in which we can see our robot takes an observation from the environment, processes it through the communication policy, and chooses which other robots must be requested the trajectory intentions. These other robots will communicate the trajectory intentions that they have computed at the previous time step, And those robots that haven't been communicated, our robot will estimate the trajectory intentions using a constant velocity model. This information will be fed into the MPC, which then will use this information to compute a control action that will be used in the environment. Then, in order to explain how our method works, we must first introduce a chosen motion planning model. To obtain the current control action and trajectory intentions at time step t, we formulate the following distributed model predictive control, which is constrained by the dynamic model and by the collision avoidance constraints. In these collision avoidance constraints, we want our generated trajectory intentions not to overlap with the other robots' trajectory intentions. However, how do we obtain these trajectory intentions from other robots? Well, this depends on whether we communicate or not, meaning that if we choose to communicate, if robot I chooses to communicate with robot J, then robot I will request J its trajectory intentions, meaning that the positions that we will use will be the actual positions computed by robot J. Otherwise, these positions will be generated by assuming a constant velocity model. However, we have a new question that arises. How do we choose whether we have to request information from other robots or not? Well, to solve this question, we must first define the robot's communication vectors, which is a set of the communication values, meaning all those communication values from robot I towards robot J that explain whether robot I requests information from robot J. We must also define the communication network configuration, which is a set of all the robots' communication vector, and we must also define the global cost of communication, which is a sum of all communication requests at time step t. This leads us to the objective of finding a communication policy for each robot that minimizes the global cost of communication while still allowing for safe navigation among robots. In order to solve this objective, to get to this objective, we formulate the following point dp, in which the state space is the same as we have defined before. The observation space is composed by the velocity of the robot, and its relative position to its goal and the other robots in the system, as well as the relative velocities to the other robots in the system. The action space is of course the communication policy. For the observation model, we consider that we can directly observe the positions and velocities of other robots, and the transition model is composed by the effect of our communication network on the computation of control input, and the effect of the control input on the transition from state st towards the state st+1. Then we define the following global reward function. In this global reward function, we reward the multi-robot system for attaining each robot its goal position, and we penalize them for colliding and communicating. Then in this work, we try to learn a parametric communication policy, in which the communication policy is modeled as a multi-layer perceptron that takes the observation of robot I as input and issues an output that in between 0 and 1. If this output surpasses a certain threshold, which in our case is 0.5, then robot I will issue a communication request, to robot J. Otherwise, there won't be any. In order to learn this parametric communication policy, we use a multi-agent actor critic algorithm, specifically the multi-agent DDPG algorithm. This is an off-policy algorithm that allows us to use a stochastic exploration policy. Also, this algorithm presents a strategy of centralized training and decentralized execution, which allows us to use all the information of our robots in order to perform the policy gradient update to update the parameters of the multi-layer perceptron. Additionally, we use curriculum learning, in which in which we add to our pool of scenarios, increasingly more challenging scenarios. The considered scenarios are those of random navigation, random swapping, and asymmetric swapping. And in order to perform the performance evaluation, we compare our method with other communication policy baselines, such as the one of full communication, in which we perform broadcasting, distance-based communication, in which we perform broadcasting within a certain radius, and no communicating. In the following video, we can see the robots in the left side, the robots navigating in this environment, and in the right-hand side, we can see how these robots perform safe trajectories while marking when they are communicated or not. As they are marked in yellow when they are communicating, and when they are not communicating, they are marked in blue. And as we can see, they learn, the communication policy learns to communicate before the intersections. In general, it doesn't communicate after these intersections. Then regarding our results in comparison with the other baselines, we can see that we managed to obtain zero collisions while still reducing significantly the number of communication requests among robots. In conclusion, we have introduced an effective communication policy that integrates the strengths of multi-agent reinforcement learning and constant optimization in certain navigation tasks. Additionally, our simulation results show that our policy learns when and which agents' intentions must be requested, reducing significantly the number of communication requests. For our future work, we intend to scale our approach to a higher and variable number of robots. Thank you very much for your attention. This is the end of the presentation.